Our second lesson for day 1 is on chords and arcs. So as always, almost always anyway, we'll have a little vocabulary here. If I have a segment whose endpoints are on a circle, so for instance, I got a circle, I got a segment, the endpoints of the segment are on the circle, then that's what we call a chord of a circle's chord. Okay, if we have an angle whose vertex is the center of the circle, so here's the center of the circle, we got an angle, okay, and there's, so let's say this is A, B is the center of the circle, C. So that angle there, ABC, its vertex is the center of the circle, we call that a central angle. Central angle. And if we have an arc whose endpoints are the endpoints of a diameter of a circle, so here's what that's going to look like. We got an arc. Hey, we haven't talked about what an arc is. Well, an arc, let me come over here. An arc is just a part of the circumference of a circle. So if I put a point here and I put a point here, and I'm talking about this part of the circle. This is an arc of the circle, and let's say we had these points labeled AB. We would call this arc AB. Arc AB. Okay, that's what an arc is, just a part of the circumference of the circle. So if we got an arc whose endpoints are the endpoints of a diameter, so hopefully we remember what a diameter is. It's twice the radius, so of course it goes through the center of the circle. There's a diameter. So if we got an arc whose endpoints are the endpoints of a diameter, so this diameter really divides the circle into two arcs, right? The green one and the red one, and each one of those is a semicircle. Semicircle. Okay, and just in case you don't remember, we're going to measure arcs in degrees. Arcs will be measured in degrees. And an entire circle has 360 degrees, so a semicircle is going to have 180 degrees. Okay, I think you probably already knew that. Okay, part of a circle that measures less than 180 degrees, so we're talking about an arc of a circle here, that's going to be called a minor arc. A minor arc if it's less than 180 degrees. And we always talk about minor arcs with two letters. So just like I did up here, AB, this is a minor arc. I can plainly see that it's less than a semicircle. It's got two letters that I named it with. That's a minor arc. All right. If we have one that's between 180 and 360, we call that a major arc. Major arc, larger than a semicircle. And I always name a major arc with three letters. So let me put another letter on this circle. Suppose I put a C down here, and then I want to talk about arc ABC. ABC there. That would be a major arc. It's greater than 180, well, but less than 360. So it's written there between, so the arc would be greater than 180, but less than 360 if it's a major arc, and it's got to be called with three letters. Okay. All right, so of course we got some theorems now. If we got a circle or congruent circles, if I have congruent central angles, then we're going to have congruent arcs. So here are my two central angles right there. If those are congruent, then I know arc AB is congruent to arc CD. That's all that says. And of course it has a converse. Okay, how about 12.5? Within a circle or in congruent circles, congruent central angles have congruent chords. We talked about chords a minute ago. You remember it's a segment that has its endpoints on the circle. So there are two chords. Okay, so if I know that those central angles are congruent, then I also know that those chords AB and CD are congruent, and I know the converse of that too. If AB is congruent to CD, then I know that the central angles are congruent. Okay, another theorem and its converse, if I have a circle or congruent circles, then congruent chords have congruent arcs. So you see how they have it colored here. If I know that BA is congruent to CD, then I also know that these two arcs would be congruent too, and the converse of that is also true. And then our next one says within a circle or in congruent circles, chords that are equidistant from the center or centers are congruent. And remember, when we are talking about equidistant, we're measuring the distance perpendicular. So if you look at the diagram here, I got the center, and the distance from the center to these chords has to be measured perpendicular. All right, and if I know those are the same, then I know the chords are congruent. And the converse. If the chords are congruent, then I know they're equidistant from the center. Okay, let's go see if we have some sample problems here. Yes, we do. What is the length of RS? RS. I'm going to highlight RS. A lot going on in these circle problems sometimes. Okay, what is the length of RS? Well, let's see what I know. Ah, look what I know. I know that RS and RP, RS and RP are equidistant from the center. The center is O. Equidistant. See, because I know they've marked it as perpendicular and they both measure 9. So therefore, because of the theorem that I just learned, I know that RS is going to be congruent to RP. And I know what RP is because it's 12.5 plus 12.5. So that means RS is going to be 25. Because it's congruent to RP, and that's what RP measures. Okay, what is the value of X? All right, well, I have, this is the converse, right? I have congruent chords. This one's 36. This one's 36. If I have congruent chords, I know they're equidistant from the center, so I know that X is 16 in this picture. I cannot encourage you enough to study these theorems and their converses. There are so many of them. Okay, next, what do we have? If in a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. So you can see this picture here, a diameter perpendicular to a chord. Then what do I know? I know it bisects the chord and it bisects the arcs. If the diameter bisects a chord that is not a diameter, then it is perpendicular to the chord. So maybe you should say these to yourself a few times. In a circle, if a diameter bisects a chord that is not the diameter, because the diameter is a chord, right? Every diameter of a circle is a chord. So think about this. I could draw this chord, and each of those diameters bisects each other, but they're not perpendicular. So the diameter has to bisect a chord that's not another diameter for this theorem to be true. If it does, then it's perpendicular to the chord. In a circle, the perpendicular bisector of a chord contains the center of the circle. The perpendicular bisector of a chord contains the center of the circle. In other words, is a diameter, right? Yeah. Okay. Let's see what kind of problems we have to look at now. Find the measure of each arc. Okay, well, I got a bunch of central angles here. And what did we learn about central angles? That the measure of the arc intercepted, we say it's intercepted. This arc, GH, is intercepted by this angle right here. And we know that the arc is congruent to the central angle. So the measure of arc GH, this is how we want to write this, is 120 degrees. The measure of GF, arc GF, is 70 degrees. The measure of arc DF is 80 degrees. Let's get one of the major arcs. We're not going to list them all, but let's take one of the major ones. How about HGD? How about the measure of HGD? Arc HGD. Well, what do I have to do? I just have to add all these up because HGD is right here. I'm going to draw it in red. HGD. There's arc HGD. So I got to add up 120, 70, 80. That's 120 plus 150, so 270 degrees. And you could get some more arcs if you want to play around with it and do that. Go right ahead. Okay, find the measure of arc KM. Let's see what we have here. All right, we got a diameter, and it's perpendicular to this chord. Therefore, we know that it bisects the chord, and it bisects the arc as well. So what does that tell me? It tells me that 5x equals 7x minus 16. So let's see, 16 is 7x minus 5x, therefore x equals 8. But that's not the question. The question is, what is the measure of Km? So the measure of arc Km equals 5 times 8, which is 40 degrees. Okay, how about the next one? QS. QS. MN is 16. MN is 16. Okay, RT is 16. Okay, so right there I'm going to stop and say, I got congruent chords. Everything I know. So I know those chords are equidistant from the center. I also know that arc MN is congruent to arc RT. I don't know if I need to know all that stuff or not, but that's what I do know. And let's see, NQ equals 10. NQ equals 10. Okay, that's a radius. And okay, so if I look at NS, if I extended that, that would be a diameter. Okay, so I know that it bisects RT. Let me think what I'm trying to figure out here for just a second. Okay, took me a second there, but I got a little right triangle, right? If NQ is 10, and I know that QP is going to bisect that chord because it would be contained within the diameter. So that means that PN or NP is going to be 8. So if you look at this little right triangle right here, I'm going to draw it in green. Look at that little right triangle. Then I have one side is 8, the hypotenuse is 10, and then I'm looking for QS, which is congruent to PQ. They're equidistant, those chords are, from the center. So what do I have? Another phone call. Okay, so what I have now, my little green right triangle, is a Pythagorean triple, right? Because if I divided 10 by 2, that would be 5. This would be 4, which means the x would be 3 times 2. So x is going to be 6, and I know that's equivalent to QS. So QS is going to be 6 in this case. I hope you haven't forgotten all your right triangle business. You will never be free of it. Okay, find the measure of arc RS. Well, same situation here, right? We've got a diameter intersecting a chord, so therefore I know that it's perpendicular to the chord. I know it bisects the chord. I know it bisects the arc. Therefore, 3x plus 24 equals 7x. So 24 equals 4x. So x is 6. But what am I looking for? I'm looking for RS. So RS is 7 times 6, which is 42 degrees. Don't forget your arcs are measured in degrees. Find HK if DG equals JL, DG. Okay, congruent chords. Congruent chords. And those are 24. And DH right here is 13. Okay, so if the chords are 24, and I know if I extended either HF or HK, that would be a diameter, so those chords are being bisected. So this length would be 12. So I got another Pythagorean triple, right? So HK, well, FH would be 5, and HK is the same. So I know that HK has to equal 5 because the congruent chords are equidistant from the center of the circle. All right, I thought it would be fun. I'm sure you will think so too. To take a sheet of paper and try to use what you have just learned about circles to try to construct a regular octagon. And it's going to be an octagon that's inscribed in a circle. Okay, I promise it's going to be loads of fun. So, of course, what you're going to do is you're going to start, I'm giving you a couple of hints here. So you're going to start by drawing a circle, constructing a circle with your compass, not just going to draw it freehand like I did. Okay, and then, actually, you know what? I don't want to spoil it at all because some of you will actually enjoy trying to do it. So please do give that a try, and we'll talk about it tomorrow if you can't figure out how to do it. And our next lesson will be on inscribed angles. We'll see you then.